Okay, we're now recording for 10 and a half minutes. The price of weakness, page 35, modeling software with finite state machines. Software is expensive. In the beginning of the computer industry, hardware costs were very high, and in relation to them, software expenses seem to be moderate. The relationship between hardware and software costs has changed all the time to software's disadvantage. Hardware becomes more powerful and cheaper. Software development tools fell behind the increasing requirements, which amplify the trend of increasing software development prices. The ever-growing software development expenses can be compensated for by the growing market. Therefore, mass-market software, such as operating systems and most of the desktop application, text editors, spreadsheets, and several utilities, is cheap as the amount of copies sold covers the expenses. In contrast, the cost of custom-tailored software reaches exorbitant levels. Because this process has been continued for many years, the whole world gets accustomed to it and accepts it as a software feature. We assume that it cannot be changed. Maintenance costs. Software does not wear out as mechanical or electrical devices do. In spite of that nice feature, software maintenance is an important and expensive activity. Because maintenance expenses are in many cases the main cost element of software, we should take a closer look at it. There are two reasons for maintenance: errors and changes. Errors are called bugs in software. Errors cannot be totally eliminated from programs. Any software contains some known bugs and a certain number of unknown bugs. The way software is designed and coded is very much dependent on a programmer's skill and is in fact handmade. Hence, it must contain errors. Automation of routine programming tasks, automation of test procedures, usage of proven libraries supported by formal design and specification methods may reduce the number of errors. At that moment, programmers concentrate mostly on debugging, that is, on searching for errors in code. When software reaches customers, the search for errors continues and is then called maintenance. During the maintenance, the customers play a very important role in supplying information about bugs. Page 36, modeling software with finite state machines. There are two types of error. Let us call them software bugs and application errors. Software bugs are errors related to the programming language, and they are made by programmers while coding, misspelling statements or variables, invalid values, logical errors, deadlocks, loops, wrong constants, wrong addresses, etc., or by translation programs, compiler, linker, loader, rather rarely today. Those bugs are the dominating errors in some programs such as text editors or translation programs or general programs, which are developed and updated over a period of many years. For those programs, the application specification is known for many years, and software companies have problems to justify pseudo-improvements and extensions that may bring money. Elimination of bugs cannot be sold as an improvement. Application errors are of a different nature. What if they could? Yeah, what if you could sell software that eliminated bugs and just track them and eliminated them? That would be very interesting. Application errors are of a different nature. They result from erroneous or contradictory requirements, misinterpretation of specifications, or just application logical errors during coding. Application errors are a huge problem in programs that are written for a specific application, often for a single customer. In case of software misbehavior, it is often impossible to identify the error type, software bug or application error. Software crashes indicate clearly a software bug. A wrong robot movement may be caused by any sort of error. Software bugs can be found only in code. Application errors can be found in code or in a specification. Software changes. Maintenance also means changes. Even if software development is based on well-defined requirements, it is just impossible to produce software that fulfills 100% of a customer's expectations. First, requirements are verbal documents whose content is interpreted. Programmers sometimes misunderstand requirements. Second, it is only by using the software that customers learn what was wrong in their specification and demand changes. Maintenance is a difficult process as it means having changes to running software. Even if the changes themselves are not so complex, the replacement of the software at a customer's premises may be a nightmare, especially if it is left to the customers. In most cases, software must be exchanged by a specialist. Software can be changed and adapted to new requirements only to some extent. Its limits are defined by its own design, and by design corruptions done during coding. While coding, we always meet situations that were not foreseen by the original software architect. We can either change the design or bypass the rules and solve the problem by using some dirty tricks. We tend to do that just once, the first time, being convinced that it is only an exception that will not spoil the nice architecture, and anyway, we are in a hurry at that moment and maybe we will improve it sometime later. We do a few such dirty tricks several times, so corrupting the software. Eventually, the software does not have any coherent architecture, and documents describing its design will have completely lost their value. I once did a search for the word friend in some software whose authors had been trying to get working for several months. I found a few hundreds of friend declarations. Any C++ programmer knows what it means. A few hundreds of global functions accessing private items, which really should not have been global. I doubted whether that software could still merit the title object-oriented, which might also explain the difficulties. Interestingly, those programmers did not seem to be innocent beginners. They were intelligent and they worked very hard. The same problem relates to a specification. Many requirement details that become apparent during the coding phase flow directly into the code. In effect, at the end, the code is the only document that contains the full description of the software. I was once engaged to write a software package that should have replaced the old one. Before I entered the company, I was, of course, told that the software would be written according to well-defined requirements. The company external image must be intact. Actually, the code of the old software was the requirement. It has been an interesting experiment for me as I learned the difficulty of enciphering what the code does from the code. Some passages were just impossible to understand. Some were just dead code, probably doing nothing useful. I learned how bad the code of old software, changed by innumerable people during several years, can be, a very interesting study of corrupted code that cannot be maintained by anyone. In code, we trust. As a rule, maintenance costs increase with time. A decisive factor is the software quality in all its aspects, specification, design, and coding. Therefore, documentation plays a decisive role. It is obvious that the only document that corresponds fully to the running software is the source code. If the specification and design are in good shape, they may contribute essentially to successful debugging or changes. Software developed without any documented method or concept reaches its limit earlier than software that can be understood without studying the code. Unfortunately, that is seldom the case, which means that the basis of maintenance is, as a rule, the code. When programmers who wrote the code are no longer available, the maintenance costs become very high. The other side of the maintenance problem is that we have to live with very old software, which is practically unmaintainable. At the end of the last century, many experts expected on January 1st, 2000, a collapse of software dependent on date. Those predictions created a demand for nearly forgotten languages like COBOL and enabled some already retired people to earn some money. Nobody knows whether the old software was really improved. Probably in many cases no changes had been required, but nobody knows the truth. The costs of software errors. It is difficult to make precise estimations of cost caused by software errors. In a NIST planning report 02 to 03, we found the following data for 2002. The estimated costs of software errors equal 59.4 billions annually. The study says that although not all errors could be removed, it is estimated that a third of them could be removed by improving testing infrastructure. The interesting but sad conclusion from reading that study is that the authors believe that only better testing can improve software quality. Obviously, they gave up the idea that better software development methods might produce better software. The programmer's world. People play a decisive role in software development. In spite of all development methods and tools, a team of programmers decides about the successes or failures of the software projects. The dependency on human skill and motivation seems in the software industry to be more pronounced than in other industries. The quality of any worker is determined by three factors: education, experience, and individual personal ability. In contrast to other occupations, a programmer's individual abilities seem to play a more important role than education. At least it is a widespread opinion. Programming is a purely mental activity interrupted by coffee breaks, so it is difficult to compensate for missing abilities by extra devotion to routine tasks. A programmer cannot compensate for a bad concept by increasing the number of typed characters per second. The quality of code cannot be measured by the number of source code lines. Sometimes we tend to believe that programming is a kind of artistic occupation. The problem with this view is that most artists have some sort of art education, generally working